With our definition of power series, notice that we have this variable x, and we can substitute in different values of x to that series. What can happen is I can plug in one value of x and the series might converge, and then when I plug in a different value of x, it might diverge. So our goal here is to look at this and try to come up with a general approach so that I can decide which values of x lead to our power series converging, as opposed to those that cause it to diverge. One thing to consider for a general power series is that the power series, which if I were going to write out the terms, it would look like c sub 0 plus c1 times x minus a plus c2 times x minus a squared, and so on. If you were to plug in x equals a, this becomes simply that constant terms c sub 0. So plugging in x equals a would result in all of the terms following c naught to go to 0 by having that a minus a factor. So we would be able to say that at the value of x equals a, this sum becomes simply the constant term c sub 0. What this means is that every power series converges at its center. So this is going to be a fact. Every power series converges at its center. So if that's true, that tells us, of course, information about one value of x. And the question we want to consider is where, if anywhere, where else might it converge? So let's look at a general power series, same thing. So consider our general c sub k times x minus a to the k. Using the ratio test, we can consider what that L value, the limit, would be. So the ratio test would give me the limit as k approaches infinity of the absolute value. Here, the k plus first term would look like c sub k plus 1 times x minus a raised to the k plus 1. And I'm dividing by the kth term, which is exactly the one that I see. Now, one thing that's going to happen is focusing on just these x minus a terms, I have an extra factor in the numerator. So that is not dependent on k. When I cancel that out, I just have a single x minus a in there. Now, what's important though is that I cannot disregard the absolute value. So when I'm writing this, noticing that I have that extra factor of x minus a, I can factor it out of the limit, but I need to bring the absolute value with it. What's left is the absolute value of c sub k plus 1 divided by c sub k. So looking at this, let's just give it a different letter. We've been calling this limit here L. Let's let capital M, actually let me use that same L. So let's let L represent, no, I'll use M because we've been using L for the general term. So let's let M equal the limit as k approaches infinity of c sub k plus 1 over c sub k. So if we look at our result there, the ratio test implies that our power series converges when the resulting limit, which in this case, our limit from the ratio test was what I have underlined in blue, which I'm now going to call, so if that limit, which I can write as x minus a times m, because that's how we're defining that limit there, if that is strictly less than 1, that's what the ratio test gives us. So I can rearrange this to say that this happens if x minus a, an absolute value, is strictly less than 1 over m. So let's give that a name. This value 1 over n, we call 1 over m, just to be clear, that's 1 over the limit as k approaches infinity of absolute value ck plus 1 over ck. This is what we call the radius of convergence for the power series. So we'll think about this when we look at examples, but thinking of the radius, this indicates how far we can move away from the center x equals a and still converge. So what we can think of here, if I want to consider a number line, we said that every power series converges at its center a. So these are values of x I'm considering. Once I think about the radius value, what we want to consider is kind of how far away from a can I move on this x-axis here and still be guaranteed convergence. So thinking of what we get from the ratio test, we know that if I have x minus a in absolute value less than 1 over m, this means that we have convergence of the series. So thinking about my picture here, that would talk about going out this distance, say. So it would be symmetric because of the absolute value. So I'm gauging this distance away from the center of 1 over m. So here I would have a minus 1 over m, and here I would have a plus 1 over m. And basically what's guaranteed in here, let's use actually the highlighter, give that a color, is that in here I have convergence. So between these markers. So that's what we get because those are the x values that cause the ratio test to yield this limit strictly less than 1. So the other thing that we can think about is the idea that instead this is strictly greater than 1. This would cause the limit from the ratio test that we looked at up here to be strictly greater than 1. So the ratio test would tell us that this leads to divergence. In my picture, that means that as soon as I go past that distance of 1 over m away from a, I'm going to be guaranteed divergence. And then the last thing we want to consider here is what about when x minus a is exactly equal to 1 over m? Turns out this is unknown. And that's because it's exactly this case when my limit is 1 with the ratio test. So what we have to think of as a consequence is that on my number line, that leads to 2 cases of uncertainty in some sense. So here and here, but those is orange, those are going to be question marks. So what I have to do is consider those on a case-by-case basis. So every time I look at a new power series, I have to consider what we think of there as those 2 endpoints and check in some way to see if we have convergence or divergence there. What I mean by that is that we can use some test that we've already seen for convergence or divergence. Importantly, not the ratio test, because at that point we would know that it would be inconclusive there. So we want to use some other test to decide if we have convergence or divergence at those points. Now, putting this all together, we've talked about the radius of convergence. That is going to be a positive number, and that's measuring distance away from the center. The other thing I want to focus on here are these intervals that I've kind of created that's collecting all the points of convergence. And we have a name for that as well. So the interval of convergence, as opposed to the radius, is, as it sounds, it's going to be an interval of real numbers, and it is for a particular power series, and this is the interval that contains all values of x for which the power series converges. So what's nice about what we've done so far by looking at just a general power series is we've done this work here that leads to this result that I kind of just can apply that to each power series that I encounter. So we have infinitely many values of x that we need to consider that we could plug into our power series. And from our work above, what we're going to be able to do is basically narrow this question down to really focusing on at most 2 points that we have to actually check each time I encounter a new power series. So that leads to the following idea. In general, the interval, in terms of what we found above, could be one of 4 things. So I could have a situation in which, so I'm going to let R represent the radius, so I don't have to write the 1 over m. So once I have the radius, again, I'm talking about these orange points that we put up here. Those are a minus r and a plus r. So it could be the case that in addition to converging between those 2 points, we find that it also converges at those points. So that would include this closed interval here. It could be the case that we have convergence at the left point and divergence at the right point. So we'd have it open over there. We could have divergence at the left point, convergence at the right point. And finally, we could have that both points lead to divergence. So there's 4 possibilities, but what's nice about this is, like I said, we go into this problem having infinitely many values of x that we have to consider, and we've reduced it to a question now of really just 2 points. So if we have this interval of values, we would have to check the endpoints. And so in order to find the interval, once I've gone through and found the radius, we must check any endpoints that we might have encountered. And again, once I go through some examples, it'll be clear what I mean by check the endpoints. And also what I hope is by going through several examples, we can really consider the different possibilities that we might encounter in terms of finding both the radius and the interval of convergence for different power series.